In this final part of this derivation, I'm going to start here and then show that this is true and then finally this. So let's start here in the second thing and also use wi that we talked about earlier. So we said that beta hat 1 was equal to beta 1 plus some I wi ui, where wi is xi minus x bar over some I xi minus x bar squared, where we're thinking about w as the weight of the observation. And then, so my objective is to first show this is true. So what I'm going to do is I'm just going to take the variance of both sides of this equation. Say the variance of beta hat 1 is the variance of beta 1, remember that beta 1 is just a constant. The variance of a constant is 0. So I'll skip right over that term. So we'll have the variance of some I wi ui. And then recall the definition of variance, like a variance of a random variable z, is the expectation. It says on average, how much does z deviate from its mean? So it's the expectation of z minus the average of z, and then we square it to get rid of negatives. That's the variance of z. So we're just going to apply that definition here. So we'll say equals variance. So instead of z, I'm just going to write this. So the variance, expectation, and it's some I wi ui minus expectation, some I wi ui. We move this to make a little more space. We square the difference there, and then one square bracket to finish it off. And then we're going to again use exogeneity. So remember when we, to talk about this term, exogeneity was that the expectation of ui conditioned on x was 0, and it implied that the expectation of wi ui was 0. So we can use that again right here to argue that the expectation of wi ui is 0 and that the sum of the expectations of all the wi ui's is 0. So that part will go to 0. What are we left with? Expectation sum I wi ui squared. And then the next step is we are going to FOIL. So what is, how do we interpret this? It's W1 U1 plus W2 U2 plus ... all the way up to WN UN, and we square it all. So this comes out to be expectation of sum I wi squared ui squared plus, let's see, then we have, just like we would have w1 squared u1 squared plus w2 squared u2 squared. So we get all of the things that match, and then we also get all the things that don't match. It would be, 2 times w1 u1, w2 u2, all of that. So we're going to say sum I, sum j not equal to I, wi ui, and then wj uj. That's what happens when we FOIL everything. And then we're going to apply exogeneity one more time. So to simplify, get sum I, expectation, wi squared, ui squared. We're going to condition on big X, because if we can show that the conditional expectation is a constant, then we know that the unconditional expectation is the same constant. Wi is just a function of X, so we can take that outside of the expectation. And by the way, we haven't dealt with this term yet, but we will. So that's sum I, wi squared, expectation, ui squared, condition on X. And this is another assumption that we need to make. This assumption is called that the fact that this is a constant, we're going to assume this is a constant, which I'll call sigma squared u. And we want to think about this as the variance of u, because u bar is close to 0. May not be equal to 0, but it's close to 0. So we want to think about this as the variance of u, and we want to assume that the variance of u is constant across X, which is also called homoscedasticity. Homoscedasticity. So that's one major assumption we need to make. Now, well, I guess I can finish up the simplification of this part. So then we'll get sum I, wi squared, sigma squared u, plus this other term. So let's work on the other term now. Oh, sorry. I've also forgotten the 2. There's a 2 here because, there's a 2. All right, so what we need to assume here, when we're taking the expectation, let's see, here, what we have here, 2, sum I, sum j not equal to I, expectation, wi ui, wj uj. We're thinking about this term as the covariance. The covariance, So just like the other side, we're going to take the conditional expectation with respect to X, because we're a little bit stuck, we're just working with the unconditional expectations, but if we can show that the conditional expectation is a constant, we know that the unconditional expectation is also a constant. Conditioning on X lets us take wi and wj outside of the expectations. So now we have 2, sum I, sum j not equal to I, wi, wj, expectation, ui, uj, conditioned on X. And we want to assume something about this term here. In particular, we want to assume that it's 0. Because this term, we want to think about it's the covariance of ui with uj. And if every observation is a random sampling of the variable, then this covariance being 0 is a given. And this is called no autocorrelation. Auto is a prefix for self. So when a variable is autocorrelated, it means it's correlated with itself. And you'll see that a lot of times with time series data. So you want to be careful about this assumption with time series data. But for cross-sectional data, this is a given, because you're thinking about each observation being random sampling. So we have no autocorrelation. That means we can assume this is 0. We can assume this is 0. It makes our life a whole lot easier because this whole term goes to 0. And now we can focus on this part. So again, what do we have here? This is the variance of beta hat 1. And we've showed it is this. What do we want to show? This. What do we need to do to get there? I think we're really close. So we have, this part is just right, the sigma squared u part. And let's look at what is sum I wi squared. Also, we can take sigma squared u outside of the summation because it's a constant. So we'll have, and remember that wi is xi minus x bar over sum I xi minus x bar squared. So we'll have that the variance of beta hat 1 is sigma squared u, and then we're squaring this, so we'll get sum I xi minus x bar squared over, we're also squaring the denominator, so let's say sum I xi minus x bar squared, and then another of that, because we're squaring it. The numerator can cancel with one of the terms in the denominator, and we're left with exactly this. That the variance of beta hat 1 is sigma squared u over sum I xi minus x bar squared.